Alright, so let's get started looking at this problem dealing with net forces, Newton's laws, and a variety of calculations. We'll get started with the problem itself. 200 kilogram bucket of Captain Crunch berries, that's so good. Being pushed along the kitchen floor, 12 newtons of force. We've got friction is at 7 newtons. First thing we do is draw the picture showing all the forces acting on the bucket. And we're going to go ahead and look at gravity, the normal, the applied, and the friction. So we'll go down here and start working on our free body diagram. So we'll take the bucket and we'll start applying our forces. We know that we have gravity working its way down, F of G. Now the bucket is not crushing into the ground and it's not floating up in the air. So we know that we have this force, this support force or normal force, that's balancing out what's going on with the gravity. We also know that we have a 12 Newton force. We'll call this F applied. We know that's going to be equal to 12 newtons. That's what we're dragging it along. Now we know that friction is wanting to work in the opposite direction of motion. That's what friction does. So we'll take a little force this way of friction. We know that this is going to be 7 newtons. All right. So there's pretty much our free body diagram showing all the forces that are going on. Now let's take up the calculations. We know that gravity is equal to the mass times gravity, or weight is equal to mass times gravity. So in this particular instance, we've got a 200 kilograms, and we're going to go ahead and use 10 to keep it easy, meters per second squared for our force of gravity. So this is going to give us a total force of 2,000 newtons. That's going to be the weight of this bucket of Captain Crunch, which is actually a pretty gigantic bucket of Captain Crunch. Okay. Now we know that because it's not crushing into the ground, now it's not floating in the air, we know that this normal force or this support force has to be the same, or else it would either be floating. If it was greater, it would float, and if it was less, it'd be crushing down. So we know that it has to be equal. Okay, now we're going to look at the forces going in the left and right direction. So these forces we're going to have, we'll call this the forces on the x direction, along the x-axis. We're going to have 12 newtons of applied force, and we're going to take away 7 of those because of the friction. So we're going to have a total of 5 newtons in this x and y direction. Okay, so that's the F of G. Now we're going to calculate our total F net. So remember, we're going to use our little sigma sign. Okay, so our total forces, we have the forces in the up and down, if you will. We'll call this the y direction. It's going to be equal to, we got 2,000 going up, and we got 2,000 coming down. Well, that gives us a great big balance, right? That's why it's in equilibrium. Now we've got our x forces. We've already calculated that. We've got 5 newtons over there. So let's total them together. The total F net for the system is 5 newtons. Because we had 5 newtons going left and right, we had 0 going up and down. The total is going to be 5 newtons. Okay, so there's our F net. 5 newtons. Right? And then the last thing it does is says we need to calculate the acceleration. Well, we know that acceleration is equal to our total net force divided by our total mass. Well, in this particular instance, we've got a net force of 5 newtons. Now remember, it's the net force. The temptation sometimes is to put the applied force or one of the other forces, gravity or something. But remember, it's the total net force divided by our total mass, which is 200 kilograms. We got 5 divided by 200 is going to give us 0.025 meters per second squared. All right, well there it is. Hope that helps. And oh yes, the secret word of the day is going to be right there. How about that? Let's make God the secret word of the day. Gotta love it. Okay, have a good rest of your learning experience.